also from UNESP, as Geraldo before, and the title of his talk is On Sufficient Optimality Conditions for Multi-Objective Control Problems.
Okay, good morning. So this work is very similar to the previous one, but now in the multi-objective problems. So part of the presentation will be, I will repeat some parts, okay, because the work is very similar. Okay, as Geraldo said, a process that satisfies the maximum principle is called an extremal process. And we know that not always an extremal process is an optimal process. So in order to distinguish a minimizing process among the extremals, we can resort, for example, to convex conditions. The sufficient conditions provided in this work go into this direction. But they are based in a kind of generalized convexity notion called invexity. Well, I will repeat some things Geraldo said. That is about invexity in finite dimensions. It was designed in 1981 for mathematical programming problems, so in finite dimensions. Okay, it's well known that the contucker necessary conditions are to be also sufficient under convex assumptions. With this in mind, invex functions were designed by Hansen in order to get the sufficiency of the contucker conditions for nonlinear programming problems. Later, Craven and Glover showed that a differentiable real-valued function is invex if and only if every stationary point is a global minimizer. However, though as demonstrated by Hansen, every stationary point is a global minimizer for invex mathematical programming problems, the converse is not true. That is, there are non-invex problems with the property that every stationary point is a global minimizer. Therefore, invex problems are the most general class of problems which possess such a property. So Martin, in 1985, redesigned Hansen's notion of invex, maintaining the sufficiency of the contucker conditions. This generalized concept of invex was termed KT invexity. And Martin proved that if a mathematical programming problem is such that every stationary point is a global minimizer, necessarily it satisfies this weakened notion, this weakened invexed condition. Summarizing, Martin showed that every stationary point is a global minimizer if and only if the problem is KT index. Okay, Martin's results were generalized in 1998 for multi-objective programming problems in a paper by Osuna Gomes and et al. Talking about control problems, we started studying KT invexity in 2008, 2009. But Aronna et al., they also studied this, and these two papers were published in the same issue. So the concept of KT invex was brought to the control context by these two works. The results in these two papers were obtained assuming differentiability of the defined function with respect to both state and control variables. Moreover, it was used Lagrangian optimality conditions instead of the maximum principle. Okay, but then in 2009, we started to study the multi-objective problem, control problem, still under the smooth assumptions, but we then used the maximum principle instead of Tucker type optimality conditions. We then introduced the notion of MP pseudo-convexity. This was for the smooth problems, and the non-smooth case was recently tackled in a paper last year. But the scalar case, now we generalized the results in this paper for the multi-objective problems, and that's I'm going to show you now. We showed then that every extremal process is optimal if and only if the problem is MP pseudo-index. Okay, here's some preliminaries. Notation, V dot W is the inner product in Rn. By this notation, we mean this inequality for each component of the vectors. V strictly less than Y, we mean this inequality for each component. And at last, this notation, we mean Vi less or equal than Wi for each component, and the vectors are different. Okay, this is classical notation for Lebesgue sets, Borel sets. GR of gamma denotes the graph of a multifunction. Gamma, W11, the set of absolutely continuous functions. Here's some basic definitions. We will make use of the limiting normal cone, and the limiting normal cone is defined like that. I won't go into the details. But we use Clarke tangent cone instead of the Bulligan tangent cone. This is convenient for us because of this relationship between the two cones, where star here denote the polar cone. Okay. We will make use of the limiting subdifferential, which is defined in terms of the limiting normal cone, and also this. This generalized Jacobian, which is defined as this set of matrices. Okay, this is the multi-objective control problem we deal with. So vector valued function G is to be minimized, subject to these constraints. So here we have differential equation, the terminal constraints, and here the inclusion for the control variable. Okay, this is classical nomenclature. A measurable function such that this inclusion is satisfied is said to be a control function. A pair XU consisting of a control function and an arc obeying the differential equation is called a process. Given a process XU, its first component is said to be a state trajectory. And we say that XU is a feasible process if X is a trajectory corresponding to the control U, which satisfies the initial and final, these initial and final constraints here. Now the type of optimality we are considering here, since we are talking about multi-objective control problems. So we say that a process X bar U bar is a Pareto optimal process, or an efficient process if there exists no other feasible process XU such that this inequality holds. And we say that a feasible process X bar U bar is a weak Pareto optimal process when you have this inequality, this strict inequality, instead of this one. It is also called and weakly efficient process. Here some hypotheses which are very similar to that hypothesis Geraldo presented. So we ask for measurability of this function, Lipschitz continuity of the vector field with respect to the state variable. The graph of multifunction U should be measurable, and the objective function Lipschitz continuous. We denote by capital H the unmaximized Hamiltonian function. And this is the maximum principle for the multi-objective control problem. So if X bar, U bar is n weak, this is stated for weak Pareto solutions. So if X bar, U bar is in weak Pareto optimal process of the problem, then there exists a scala, lambda, a non-zero vector, omega, and an absolutely continuous function p, such that we have these four conditions satisfied. The first one is the adjoint inclusion. The second, the Weierstrass condition. Here we have the transversality conditions, and at last, the non-triviality of the multipliers. I would like to remark that this inclusion, the adjoint inclusion, can be equivalently stated as this inclusion. So instead of using the convex rule of the limited subdifferential of the Hamiltonian, you can state it as in terms of the generalized Jacobian of the vector field F. Also, the theorem was stated for weak Pareto optimal solutions, but as every Pareto optimal process is a weak Pareto optimal process, the theorem, the maximum principle above, is applicable to Pareto optimal solution as well. Okay? So the theorem is valid if we're talking about weak solutions, weak Pareto solution, or Pareto solution. Okay. Some more definitions. When you have this triple satisfying the conditions from the maximum principle, say that X bar U bar is an extremal process, or also an stationary process. When lambda equal to 1, we say that it's a normal extremal process. Here we have the same notation Geraldo used before. Delta alpha of F is this difference here. We also use this notation for the Hamiltonian. Now I will present the MP pseudo-convexity for the multi-objective control problems. And I'll present also the optimality conditions in terms of these generalized convexity conditions. Okay. We have two definitions. One of it is appropriated for two normal problems, and the other one, which is more general. And the difference is that when we define MP pseudo-convexity for normal problems, we do not have to involve the multipliers into the definitions. And if we define it for general problems, then we have to involve the multipliers into the definition. Before the definition, I have some words. Let us remember that the concept of MP pseudo-convexity was designed for optimal control problems. The same reasoning, KT convexity, was developed for mathematical programming problems. And let us remember that KT convexity is to be applied for Kahn-Tucker points. That means we are talking about stationary points for which the Lagrange multiplier associated with the objective function is positive. Then it's natural that NP pseudo-invex is a sufficient optimality condition only for a normal extremal process to be an optimal one. So I will present this definition for normal problems. The second definition, which involves the multiplies, it's very similar to the definition Geraldo presented. So I will only show you this first definition, which is more suitable for normal problems. This is a proposition which is an auxiliary result for us to establish one of our main results, but it can be seen also as a characterization of extremal processes. So let alpha be a scalar in the 0-1 interval, x bar u bar a feasible process of the problem. Assume that given a generalized Jacobian gamma of the multiobjective function and generalized Jacobian zeta of t of the vector field, for any pair of, I think I skipped something, sorry. Here, exactly. I skipped this slide, sorry. Before the proposition, I should define the set of alpha feasible direction, which we denote by f alpha of x bar u bar zeta, where x bar u bar is a feasible process and zeta is a generalized Jacobian of the vector field. So this is the set of all pairs y, v, such that these three conditions are satisfied. So we have a kind of linearization of the dynamics of the problem. But here, so see that we are using the generalized Jacobian of the vector field, but here that delta alpha, a kind of variation on the control variable. Y of s, y of t belongs to the tangent cone to C at this point, and this variation on the reference control U star should belongs to the set U of t. So this is the set of alpha feasible direction. And now the proposition. If given a generalized Jacobian of the objective function, a generalized Jacobian of the vector field, for any part of alpha feasible direction, we have this inequality. For at least one j, then we are able to show that x bar u bar is an extremal process of the problem. Okay, this is a technical lemma I will skip. This is the definition of NP pseudo-inversity for normal problems. So here we do not involve the multipliers. Remember that Geraldo used a set, capital gamma, which is a set of multipliers. So here, for this case, that set is not necessary. So let us take a look on the definition. Let x bar u bar be a feasible process of the problem. The problem is called multi-objective control problem. CP is said to be NP pseudo-invex at x bar u bar if for every feasible process xu with this inequality and all alpha in this interval given a generalized Jacobian gamma and a generalized Jacobian zeta of t, there exist maps eta and xi, which are alpha feasible directions, such that for each j, we have condition 6. Observe that as we have this inequality, so for each component, we should have this or this. If we have this, then this inequality should be satisfied. If we have this strict inequality should be satisfied. Okay, this is the definition for NP pseudo-invex at x bar u bar. When the problem is NP pseudo-invex at every feasible process, we simply say that the problem is NP pseudo-invex. Here we will need of this hypothesis. So let W be a non-zero vector, which belongs to the positive orthant. We say that hypothesis H of W is satisfied if the intersection of these two index sets here is non-empty, whenever XU, X bar U bar are feasible process with this inequality. This is the theorems where we have the sufficiency of the MP pseudo-inversity. So let X bar U bar be a normal extremal process of the problem with multipliers 1 omega p. Assume that the problem is MP pseudo-invex at X bar U bar and H of omega holds. Then X bar U bar is a Pareto optimal process of the problem. In the case of weak Pareto optimality, this hypothesis is not necessary, so we have exactly the same theorem, but for weak Pareto optimal process, and this hypothesis is not necessary. Now, a variation of that hypothesis, we say that hypothesis H is satisfied if that the intersection of the same index sets is non-empty whenever XU, X bar U bar are feasible process of the problem with this inequality, and X bar U bar is an extremal process with multipliers lambda omega p. Assume that the problem is MP pseudo-invex and H holds. Then every normal extremal process is a Pareto optimal process. Again, in the case of weak Pareto, H, the hypothesis H is not necessary. Now the converse results. Assume that the problem is such that every extremal process is a Pareto optimal process. Then necessarily it is MP pseudo-invex. So this is a corollary of the last two theorems. Assume that the problem is normal and that hypothesis H holds. Then the problem is MP pseudo-invex if and only if every extremal control process is a Pareto optimal process. So here we generalize for multi-objective control problems the result from Martin. Here we have a remark. Observe that theorem 6 is the converse of theorem 4. And I did not present the converse for theorem 5, which is about weak Pareto optimality. So I have this remark. The converse of theorem 5 is not valid, so that a similar result as corollary 1, this equivalence here for weak Pareto optimality does not hold. However, if this condition, which appears in the definition of MP pseudo-invex is changed by this one, then we are able to establish the converse of the theorem 5 as well as a similar result like corollary 1. Well, as I do not have much time, I think I will stop here. I will not present the general case, but the general case was presented by Geraldo for state-constrained problems. So it's very similar to in this case. Let me skip this. Here's some references. The papers I mentioned, I cited during the talk. The paper by Hansen, the paper by Craven and Glover, the paper where KT invex was introduced, the paper by Martin. This was generalized for multi-objective problems in this paper. This KT invex was brought to control problems context in this paper and this one. We first studied multi-objective control problems in this paper, but in the smooth case, the non-smooth case was treated here, but the scalar case, not the multi-objective case. In this paper, you can find a maximum principle, the maximum principle for multi-objective control problems. And I put here the book by Winter, where we can find it's a good reference in optimal control problems and non-smooth analysis, as well as the book by Clark and the book by Mordkovich. These are classical references. So, in the end, thank you for your attention.